Yeah, let's see. So the first one is actually trivial. So what the first one wants you to realize is that you can do the whole thing backwards. So you can start with closed sets, and then you can get a topology from the set of closed sets, right? And I'm not really going to do it. It's just x and phi are there. That's complement. So it's yes, x and phi are in C, so it's there. Finite unions and arbitrary intersections. So finite unions translate to arbitrary intersections, right? And vice versa essentially. So x minus intersection C translates to union x minus C. And because of that, it's a topology. So essentially, it's a reverse of theorem 17.1. So nothing much to discuss here. And yeah, that is the lemma you need to show that it can be done backwards. Yeah. Show that if A is closed in Y, and I've already done that. So it's in the theory portion. Okay. Yeah, this one is interesting. So A is equal to A is closed in Y, X, and B is closed in Y. Okay. So this and B is equal to X minus V, essentially, right? And U and V are open sets. So yeah. Now A cross B is equal to X cross Y. Sorry, X. Hang on. Yeah, X minus U cross Y minus, right? And if you check section 1, I have proved that this is equal to X cross Y minus, I think you can go either way, it doesn't really matter. Yeah, let's hope this is the way. Uh, Minus V cross, right? Yeah, right. Either that or the other, it doesn't really matter much here. Yeah. So know that both of these are open sets, right? So we just have to show that this is an open set in an arbitrary topology, right? That's all we have to show. So for this, you just show that it's equal to X minus, U union V, right? And how do you show that? Well, you just decompose the logical formula. It's another set theoretic exercise, but I'll just write it down for you. So it's bracketed, but the and still transfers over, right? So you can rearrange the brackets here, and then you'll get X belongs to X. Uh, so and X does not belong. Um, so not of X belongs to U or X belongs to B, right? Yeah. So these two are the exact same thanks to the logical De Morgan's law, right? So you just have a not here and that. So what does that mean? That means this and these two sets are the exact same. And you can even check it in another way. Well, let's say if it's in U, it will be removed. If it's in V, it will be removed. If it's in neither, it will stay. If it's yeah, same thing here. So because of that, well, since U and V are unions of open sets, it's going to be an open set, and therefore you're subtracting from an open set, and therefore you get a closed set. And in a similar argument, but here, since these two are open sets in X cross Y, A cross B is a closed set. So we're done. Okay. Now what now? So using the same argument, we'll be able to show that A minus U is closed since A is equal to X minus V and X minus V minus U is closed. So we just showed that. And U minus A is open. Yeah, that's a little. So U minus A. Um, yeah. So let A equals X minus V. So U minus X minus V, right? So I'll try to show that this is equal to U intersection. Is it intersectionally? Yeah, it's intersection. And this is clearly an open set. So if we show that these sets are equal, then we're done, right? Yeah. So how do we show that it's equal to that? So if it's in U and V, it's going to stay here and it's not going to be removed, right? We're not removing V from it. So it's still going to stay. So we're done. Now for the other one, if it's in U, it's going to stay in U and are we removing V from it? Okay. Okay, I'll just write it down to the formula. So I didn't really have to do it this way. That X belongs to U and X not belongs to X. Note that this is a subset of X, so you do actually have an implicit X belongs to X here, and that's the key. So not X belongs to X, and X does not belong to V, right? And this thing translates to essentially X belongs to X, or X not belongs, uh, either and or. Uh, okay, so this stays no matter what. Essentially. So even if this happens to be here, we just don't care. Yeah. So yeah, X belongs to U, and let's see. Hmm. So the not changes this to X not belonging to X or X belonging to a V, right? So yeah, since this would essentially lead to the empty set, we ignore it, and yeah, and if both of them are not true, then we just get the empty set. You have to use some sort of implication, but yeah, it probably is equal to U intersection V. I'm just a little stuck on proving it. I think this is it, but that's it. Hmm, I guess it should work though. Yeah, like this is the motivation essentially, and not of this. So I, yeah, you know what? I'm going to cheat here and remove this, and it will all work. So yeah, great. Then it turns into this and X belongs to V. So you know, I'm not sure. So it has to actually belong to X no matter what. So that cannot really be removed. So yeah, the logical formulation is a bit incorrect, and I will not work on it. But that's a rough idea of it. So to show that they're equal, use some other method. I don't know. Fine, whatever. X minus V. It's not an X minus, right? So it's, I guess you can prove this is equal to U intersection V complement. We're done, or more like X minus V complement. And this is an actual formula, but this only works if both of them are subsets of X. So you have to work accordingly. So this works precisely because it's a subset of X. So you have to take that into. Yeah. But this formula is true for subsets of a big set. That's for sure. So if we're taking the relative complement with respect to that big set, we're all fine. And note X minus V was arbitrary. So yeah, if you can use that formula without cons, given the conditions I just mentioned, then. But yeah, okay. So I think I proved that closed interval a comma b is a closed set. So in case you didn't get it, it's very simple. This is an open set, right? Let's see, and its complement is equal to this by the definition. No. what it means to be an order and closed interval. So it's a complement of an open set, and therefore this is closed, and it contains a comma b. And what does that mean? That means, well, it's a closed set containing this. So it's definitely going to contain the closure. So we're done. Now, under what conditions does the equality hold? Let's see. So yeah, if A has if A has an immediate successor, right? So let's call it C, right? So then closed interval C, comma B open is equal to A, comma B, correct? Right. So in that case, what will end up happening is, and same thing here, if B has no immediate predecessor, sorry, it does have an immediate predecessor, then C, comma D, which D will be the closed interval. You can check that this and this are the exact same. So then A, comma B happens to be a closed set. So then so yeah, under this condition, what's actually happening is that A, comma B whole closure is equal to A, comma, since it's actually a closed set. So this happens when A has an immediate successor and B has an immediate predecessor, right? Now, if that were not to be the case, then I'll show that the point A and B have to lie in the closure. So a lot of the exercises are going to ask you to check whether one point belongs to the closure or not. And for that, we use theorem 17. So take any arbitrary neighborhood of A. So that's going to be, A minus epsilon. So yeah, that only works in the real line. Yeah. Okay. So essentially, yeah, the equality holds when there is no immediate predecessor or successor of A and B respectively. Yeah. So if C is, so let's say C is an element that's greater than A and less than B, which has to exist. We're assuming it's non-empty. If it's empty, then well, the closure is what? The closure is empty too, since phi is a closed set. So we're assuming it's non-empty, and it's not a predecessor too. Then any neighborhood that yeah. So if every neighborhood of A is intersecting the open interval A, comma B in some point, right? That can only happen if yeah, it's intersecting at some point, right? So if the intersection is never empty, that can only happen when there is no predecessor. Because if there is a predecessor, then it would there exists a neighborhood. We just identified one. Uh, in this case, it would be C, comma minus infinity, that such that it's not intersecting the set at all. Because C is the immediate predecessor, and by definition, the set A, comma C will be empty. That's the definition of immediate predecessor successor. So what does that mean? That means if this condition is violated, we have A in the group, and similarly for B. So yeah. Okay. Okay, this is relatively simple. So question 6a. So B closure is a closed set by definition, and it contains B, which contains A. And therefore, A closure must be a subset of B closure, as A closure is the intersection of all sets that closed sets that contain A. So it must be contained. That's it. So essentially, all the answers of question 6 can be answered can be obtained through the definition of the intersection definition. And for question 8, we use the limit point definition. So yeah, let's do that. So A union B is equal to A closure union B. Okay, so same argument here. A closure union B closure is a closed set because of finite intersections. and it contains A union B, since it contains A and B, so it contains A union B. And what does that? That means A union B closure has to be contained in this, right? So we're done in one direction. Now for the other direction, A union B closure contains A closure since A union B contains A, and similarly it contains B closure, and therefore it contains the union. So yeah, both directions are done. Yeah. For C part, the one direction is similar to the B part. So essentially, even if this goes on arbitrarily forever, it still works out because that's how unions work. The closures, sorry, if it contains every single member, then it contains it. So that thing works out arbitrarily, and that's why the C part is also proved in the similar way. But for the counterexample, I'll give you. So in the metric topology, it's quite intuitive. You just take what, open circles. I'm not going to state this as the example, but yeah, you can just take open circles, and if they're of the form, let's see, we're taking unions, right? Yeah, 1 minus 1 by n, and you just expand until you know take all of them. It's their union is, oh right, open circles. Yeah, that. Yeah, actually, if you take the closures and then take their union is going to be an open set, but so it's going to be open B of radius 1. And if you take the union and then the closure, then it's going to be closed B 1. So that outer ring is missing. And that's why it's a strict technical. But I'll show you an example in the order topology now. So for that, essentially we have A and B, and we have A plus 1 by n. So something here, and it's going closer, comma B minus 1 by n, right? Yeah. And its closure will be closed, intervals, and it's going to increase, and the union is actually going to be an open interval A comma B. But if we take the union, it's going to be A comma B because that's how the unions work. And its closure will be closed interval A comma B. So it's a similar example, but in the order topology itself, we can get such a example. Such an example. So yeah. Okay. Yeah. So the proof is wrong at the very last line. So it's attempting to use theorem 17.5. I was about to write 17.5 there. Yeah. And this part is fine. It must intersect some neighborhood. But after using theorem 17.5, it's saying that X belongs to A alpha. So we're changing sets in the middle, and that cannot be done. So if you're using it, at least use it correctly. So yeah, it said this implies this, which is dead wrong. I mean, okay, or at least it's using the condition here to change it for another set and then imply that. Either way, it's starting to use 17.5 for this set, which is closed fine, but then it's reaching the conclusion for this one. So you can't do that. And my example also illustrates why any proof should be wrong. So yeah. Okay. Now for this one, so I'll give examples first, why every inequality is strict. So question 8, let's see. Yeah. So note that B is a closed set, A is a closed set, so that's not going to help. Yeah, I think this is a pretty good example for all of them. So if we take minus 1 by n and 1 by n, so no, they are two separate sets. Hang on, yeah. Yeah. So their intersection is 5, right? But their closure is including the point 0. And the intersection of their closure is actually also the single point 0, right? And we're using the standard topology here. So we have 0 and 5. And this also holds for, I believe, one of the others. Yeah. So this also holds for C part, right? For C part, what do we get? We get, yeah, we also get 0 on one side, on the left side, and pi on the other. So strict containment. And for the other one, yeah, it's also the same inequality. So if we prove the first one, then the second one, since an arbitrary intersection can also be written down as a finite intersection, so it'll be fine. So let's prove them all now. Okay. Yeah. Okay. So essentially, um, A is going to be contained in both, B is going to be contained in both, and the limit points of A that are not in B and the limit points of B that are not in A are also going to be contained in both, but the limit points that are in both are not going to be contained. That's surface level. But note that this is precisely what makes up the intersection. There's got to be a better way for this. Yeah, so there is a better way to do it. So A is A. Okay, yeah. So A is a superset of intersection B, and B is a superset of A intersection B. So you can see where I'm going with this. A, so closure, 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 and their intersections also line up. A intersection B is also a superset of A intersection B, right? Yeah. And the same thing holds for the general version, right? And for C, let's see. Yeah, I'm gonna have to do some trickery. Yeah. Okay. So A closure minus B is going to be a superset of A. First of all, which one is the bigger one? The second one's the bigger one, right? Right? Yeah. Okay. So this is the case, right? If the second one's the bigger one, this isn't. Yeah. Okay. Which one did I just do? So A and B, the answer is essentially yeah. So this one, this part is included in the first one, right? Yeah. So this one's bigger. Yeah, let's prove it. Okay. Hmm. So A minus B closure. Okay, so does A closure minus B closure contain? So it definitely contains A. Now, does it remove all points? Okay. Hmm. So, okay, this isn't even a closed set, so we can't do much about it. Hmm. Okay, this closure is definitely contained. Yeah, I don't know. Yeah, so there is a better way to solve them, and I worked it out. I'll just explain it. Yeah, let me do it again. Okay, so first one, A is a superset of A intersection B, no matter what you take. So A closure is a superset of A intersection B, and the same thing goes for B essentially. And because of that, A intersection B, A closure intersection B closure is a superset of A, and this argument holds in generality for an arbitrary collection of sets. So A and B part is solved this way. are solved this way. Yeah. Now for the other one, for C part, we need to be a little bit creative. And yeah, here's the first time we actually need to use either theorem 17.5 or the limit point definition. So yeah, what I'm going to show is that if X is not in this set, then X won't be in this set. And the contrapositive is essentially saying that this is a subset of this, which is what we have to do. So, yeah. So for that, let's see. It's pretty easy. Now this one is equivalent to saying that exists an open set of X, so neighborhood of X, such that U intersection A minus B is equal to empty. The empty set. Yeah, is empty. So what does that mean? That means that, well, X, uh, from this we can conclude that X is a limit. X belongs to a closure, but X cannot belong to B closure. So it's this or X is not in B closure. Either one of them works, right? So from this, we can conclude that X does not belong to what? A closure minus B closure. Yeah. Does it work out? No, from this, no, it doesn't. Actually, wait. Sorry. Yeah. Yeah. Okay. So from combining these and negating them, we get, because the OR turns into an AND, this becomes into a positive, this becomes into a negative. So yeah, I think I'm missing something up. Let's see. Okay, so there exists a neighborhood of X, this X, such that it intersects A minus B, right? Let's make it up. So A minus B this set, and it's intersecting this set. So there exists a neighborhood. Oh, sorry, it's not intersecting. Yeah, yeah. So X's neighborhood is not intersecting this, so it can intersect this. There's no problem, right? So it actually doesn't care about it. It cares about intersecting that. Hmm. Now, if it intersected both of them, then what? Then would it care? Um, yeah, it wouldn't care because yeah, because then yeah, it would essentially be deleted out. That's fine. So or X belongs to B closure. That's fine, and X cannot. Actually, yeah, wait, that's. Mm, oh, okay, yeah, my bad. This was fine. Yeah, because yeah, I just yeah, this is a bit confused. X, so X cannot intersect A, so X does not belong to A closure. And if it belongs to B closure as well, if it doesn't also belong to B closure, it doesn't care. If it belongs to B closure, then it doesn't have to belong to A closure. That's fine, right? If it does belong to A closure and B closure, then we don't care. So or X uh, belongs to B closure. Yeah. Okay. So yeah. So this entire thing means that, well, yeah, just it does indeed translate to X does not belong to A closure minus B closure, because there's a not here and there's a not and here, it does flip out. So you'll have to work in the hardware, the logical framework. But yeah, these two statements are indeed equivalent. So we've proven this, and from the contrapositive, we've proven that it's a subset. Yeah. Should I try that? No, I will not explain why they're equivalent. You have to say. But they are equivalent. I am pretty sure of that. Yeah. Okay. So show that A cross B closure is equal to A closure cross B closure. Okay. I think, yeah, we can work in the similar way. So if X doesn't belong to A cross B closure, then there exists a neighborhood U of X or a basis element. It goes either way. Yeah, I'll just use the basis element directly such that X belongs to B and what? And actually, that's exactly what it means to be a neighborhood. So this can be removed. B intersection A cross B is empty. Yeah. Okay. So, oh, this B is a bad idea. I'll use S for the basis element. Okay. So now what? Now, so I'll call this S as U cross V, where V and U are open sets in A and B, right? So is it? Are we working in a subspace? Oh yeah, we are working in a subspace. No, we're not. Um, they are open sets in X and Y. Yeah. Okay. So now what? Now these allow us to find. So this X is actually this way. Yeah. This is equal to Z. I'm just writing it as Z here, and this is equal to X cross Y, right? And this U must enclose X, otherwise it won't enclose X plus Y, and this V must enclose Y. So now what? Now this U and V are X belongs to U and Y belongs to, and this is an if and only if statement. Okay. Now what? Now, yeah. So because of this, we have shown that X does not belong to A closure and Y does not belong to B closure. Now we just, yeah, I'll just show that this goes both ways. So if X doesn't belong to A or B closure, there exists a U and V such that its intersection with A and so observe that U intersection A is also zero, right? Phi is called zero sometimes, and yeah, so it goes both ways essentially. V intersection B is also phi, and that implies that U cross V intersection A cross B is phi. That's also an if and only if statement. You can check from the distributive property proved in the exercises. Essentially, the intersection goes inside, and I've used it before. What else? Then, yeah, from that we get backwards. So it goes both ways. And using the knot, we can flip them around, and from the contrapositive, we get that they're both subsets of each other, which means that they're equal. So yeah. Okay. Show that every order topology is Hausdorff. That's pretty simple. Let's see. Okay, so let x comma y be 2 points in the set X, and without loss of generality, let X be greater than Y, right? Okay. Now there are two cases essentially. X, the set of points Z less than greater than Y and less than X. This set can either be empty or not, right? And if this is empty, then Y is the immediate successor of X. And in that case, by definition, since we've assumed, by assumption, sorry, Y comma infinity and minus infinity comma X are disjoint, right? Since we assume this is empty. Since they're disjoint and they're open sets, we just yeah, for any arbitrary pair, we just got the Hausdorff property. Now, if this isn't empty, then we just simply replace x and y with z, and we're done. So yeah, the order topology is Hausdorff. This might actually be the trickiest of them all. So the other two should be easier. Let's see. Yeah, the product of two Hausdorff spaces is Hausdorff. So x and y are two Hausdorff spaces, and we have to show that x cross y is Hausdorff. So let x cross y not equal x prime cross y prime. So this can only happen when x is not equal to x prime or y is not equal to y prime. So we'll just work with either case, right? Now, since x is Hausdorff, there exists ux and ux prime such that their intersection is phi, and x lies in ux and x prime lies in ux prime. So because their intersection is phi, ux cross. So we don't care if they're equal or unequal. So we just have uy and uy prime. So if they're equal, we'll just have the same common neighborhood. If not, then we'll have the separate ones. It doesn't matter. You can the argument holds for both cases. You can pick any one and essentially take any neighborhood that contains both of them or doesn't, contains one of them. It doesn't matter much. But the point is, these two sets is intersection is also empty just because of this set. So if phi is multiplied with any set, the resulting set is also the empty set. Hence, that one line about the discussion becomes empty as well. So yeah, and note that this contains x cross y and this contains x prime cross y prime. So we'll have to make such a set, but there always exists such a set because so in this case we can just take y itself. That also works. And yeah, in that case we can take x itself. Yeah, I was thinking too much, but yeah. And one of them must happen because they're both sorry, they're unequal. Otherwise, they'll just be equal, and the assumption doesn't. So the hypothesis has to be true for the hypothesis, the Hausdorff checking. Yeah. Okay. So the subspace of a Hausdorff space is Hausdorff. So A is a subset of Y, and A comma B is in A, right? Now, by transitivity, A comma B also belong in Y. So there exists UA and UB, right, which are open in Y and disjoint and so on. And note that if you intersect both of them with A, they become open sets in A, and their intersection remains empty because their intersection is empty. So yeah, and that allows us to make show that it's Hausdorff. Okay. Yeah, show that X is Hausdorff if and only if the diagonal is closed. Okay, this was tricky. I think I screwed up when I attempted it for the first time, but luckily I solved this before recording, so I do know what to write. Let's see. Okay, so X is Hausdorff, right? We just proved that X cross X is Hausdorff since X and X are Hausdorff, right? Okay, now, yeah. So let X not equal to Y, right? And that means X cross Y does not belongs to the diagonal, right? Okay. Now, if we show that X cross Y does not belong to this implies that X cross Y does not belong to the closure of the diagonal, right? So we're going to use the theorem 17.5 for that. If we show this, then by the contrapositive, we show that the diagonal is a subset of the diagonal's closure is a subset of the diagonal. And that precisely implies that the diagonal is closed. So we'll be done. Yeah. So to show this, I'm going to use the equivalent statement, which is what? There exists W of x cross y such that what W intersection diagonal is empty, right? So if we show this, then we're done. So for this, now we're going to use the Hausdorff hypothesis. So ux and uy, their intersection is phi, and x belongs to ux, and y belongs to uy, right? We've got all that. Yeah. So now I am just going to show that. So ux cross uy is a is an open set of x cross x, right? Yeah. Now this actually cannot. This is precisely our open set W such that it's not intersecting with the diagonal Y, because if let's say Z cross Z happens to lie in UX cross UI towards a contradiction, right? So now what? Now that means Z is common in UX and UI, which is contrary to our hypothesis. So yeah, that means it cannot intersect with the diagonal. And because of that, we're done, essentially. So yeah, that was one direction. Okay. Now let's say the diagonal is closed in x cross x, right? So that means it actually, yeah, it's the exact same argument, but you just change it a little bit. So yeah, okay. So the diagonal is closed. That means yeah. So x belongs to. So this essentially is equivalent to saying that there exists a W such that x belongs to W. Open in x, open in x cross x, sorry, and W intersection delta is phi, right? Yeah. Now, actually, yeah, you don't even need W here, or I can just consider W to be a basis. So it's going to be made up of U cross V, right? And yeah, and this exists for all x essentially, right? Okay. So yeah, I'm just going to prove it directly now. Let x not equals to y in x, right? Now, hmm. So x cross y does not belong to the diagonal, right? Hang on, sorry. Yeah, this is actually for all w. So I'm a little bit off here, but don't worry. So this was just, yeah, not of this set. Okay. So let x cross y does not belong to the diagonal, and therefore it hang on. So the diagonal is closed. So actually, I just consider them equal, right? So this implies x cross y does not belong to the diagonal closed here, right? Now, yeah, from that we get w, which is a basis element, so it's going to be made of u cross v. We can consider either way, given the equivalence of 17.5. Now w is equal to u cross v, and it's not going to intersect the diagonal at all. So yeah, u is a neighborhood of x, and v is a neighborhood of y, and their intersection cannot have a common element, because if it does, then z cross z is in the diagonal, and therefore it's intersecting it, right? But that's contrary to our assumption, because this is closed. In fact, yeah, from this onwards. So because of that, u and v are disjoint, and u contains x and v contains y, because w contains x plus y. So yeah, that is the Hausdorff property precisely. Yeah. Okay. Is the finite yeah. So the answer is every single point, and I screwed this one up too. So why is it every single point? So take an arbitrary real number, right? So take a UA, it's going to have all but finitely. So you take any arbitrary neighborhood of any real number, every it's going to have all but finitely many points of the sequence. And that's precisely what it means for the sequence to converge. So yeah, that's pretty much it. And it has to have all but finitely many, because if it does uh, actually leave out infinitely many of the points, then what will happen is that it's not an open set. So we're only considering neighborhoods for reason. And in the finite complement topology, yeah, that's just how it works. In the countable complement topology, we would have a problem, because you can leave out the entire set here. So yeah, it might actually converge to no point then, but not worth discussing. So yeah. Okay. Show that the T1 axiom is equivalent to that condition. Yeah. Okay. So let's see. So T1 is basically saying that finite these sets are closed, right? Yeah. Okay. So let x not equals to y. That is important. Otherwise, it doesn't matter now. And x and y are both in x. Now what? Now let's see. Yeah. So yeah. So given that singleton x is closed by assumption, and singleton y is closed by assumption, x minus singleton x and x minus singleton y are both open sets that don't contain the other point. So we're done. It said nothing about their intersection being empty. So we can actually have it. And it doesn't contain the other point. So we're done. So yeah, one direction is pretty simple. For the other one, we just have to prove that single point sets are closed again, right? Right. Okay, let's show that. Mm, so to show that, we just need to show that for every x in x, this is closed. Then we'll be done, because finite union of closed and sets are closed. So how do we show that? Well, let's consider y not equals to x, and from that we get there exists a open set y such that x does not belong to open this uy, right? So there exists such an open set. So now what? Now you take the union of all such y. So y belongs to x minus singleton x essentially, and uy. Since this is an arbitrary union of open sets, we get an open set. And since we're considering all members of x minus singleton x, what does that mean? That means every single member is going to lie here. So from the same trick as earlier, this is equal to singleton x's complement. So we just showed that this is an open set, but that means this is closed. So we're done. So yeah, consider this, determine the closure under each of these policies. So let's go. So to find out the closure, we're going to have to use theorem 17.5 both ways. So if it's in the closure, we're going to use the negative. If it's not in the closure, we're going to find a counterexample. Yeah. Okay. There you go. Let's see. The standard topology, that's pretty easy. So in the standard topology, I think it's already discussed, but it's 0 union K. We're done. For the topology of RK, yeah, we have, so R minus K is an open set. You can check that since you just take, well, minus 1 comma 1 minus K, that's an open set. And then you just take the union of every other open interval, right? So you just take, actually, yeah, 1 comma infinity minus infinity to minus 1. So union of 3 open sets, it's an open set, and that's precisely R minus K. So yeah, it's an open set. And this open set contains every point other than K. So the closure of K in the RK topology is K, since K has to be contained in the closure always. So yeah, and this leads to the this leads to a motivation towards the theorem that if we have a finite topology, then the closure is smaller, right? And I'm not proving it. It's the idea behind the proof is essentially that we have a more open sets to check from. So in fact, yeah, you use the definition of belonging to the closure, and from that you can show that you are less likely to find the open set that you want to eliminate the suspect, the closure belonging members, and because of that, you're going to get a smaller closure from a finite topology. So yeah, you can show that. Finite complement topology, I believe it might just be every single point ever. Let's see. Yeah, so any open set is going to intersect. Yeah, any and all open sets of the finite complement topology are going to intersect K. You cannot avoid that. So yeah, it's the entirety of R in the finite complement topology case. In fact, yeah, it's also discussed in question 14. So we're done. Yeah, kind of. It's kind of discussed. They're not completely. The definitions are close to each other, but not completely equivalent. Yeah. The upper limit topology. So here, yeah, since open intervals are there in the upper limit topology, so the only suspect we have is 0 union K, right? So it has to be a subset of that from the theorem I just mentioned that you can try proving on. So 0 won't be there because, well, closed interval 0 comma, well, even infinity minus infinity. This is an open set that's containing 0 and does not intersect K. Because of that, we have 0 not being in the closure of K in this topology. Last but not least, the topology having all sets minus infinity to A as a basis. Let's see. So is 0 going to be here? Well, 0 is here because so it works in reverse too, right? This is clearly coarser than the standard topology. So at the very least, 0 has to be there, right? But okay, so is any number less than 0 going to be there? No, because you can always find an interval. But the thing is, every number greater than 0 is going to be there. Why? Because you take a single number greater than 0, you're going to find the 1 by n that's in it, and it's going to lie in this interval. So if let's say we take B and B belongs to minus infinity to A, so there has to be some neighborhood you choose from. 1 by n is going to be there, so it's going to intersect it. And if it's beyond 1, right, it's intersecting all of A. So you have to consider all the open sets, and these are actually, so hang on, the basis, right? Yeah, so their intersection, because we don't have A comma infinity, we'll never actually achieve you know, a closed interval. Sorry, an open interval, I meant. Yeah. So we're never going to get the interval we want. So we essentially only have pretty much the entire topology is only made up of rays and these type of rays. Yeah. And that's because you take any arbitrary union of these rays, you're always going to get it. You're not going to get anything else. So the entire topology, in fact, the topology having these sets as a basis is having these sets as open sets as well. Let me just check that. Yeah, I think so. Yeah. So because of that, there is not a single open set that you can find that would include a point other than K that's also greater than 0 that would also, not intersect K at all. So yeah. Okay, now which of these topologies satisfy the Hausdorff axiom and the T1 axiom? So the standard is satisfying the Hausdorff axiom, and yeah, so any any topology that's finer than the Hausdorff, and then a Hausdorff topology will be Hausdorff. So that means RK and the upper limit topology are also Hausdorff, right? The finite complement topology is not Hausdorff because it just converges to multiple points, and it's T1 because literally that's how it's defined. The topology having that as a basis is not Hausdorff because, well, you just take any x and y. You're not, and if x is, let's say, less than y, you're not going to find a single neighborhood of y that's not intersecting x. So yeah, this is not even T1. Wait, yeah, this is not even T1. So yeah, and if it's not T1, it's automatically Hausdorff because yeah, that's how implications work. Okay, what's next? Yeah, we have another closure problem. So yeah, the method is the standard one. So use theorem 17.5. But yeah, it gets tougher and tougher because you have more and or less open sets to consider. And yeah, so we have the lower limit topology and the rational lower limit topology, and that's what I'm going to call it. Yeah. So it's clear that since both of these topologies are actually finer than the standard topology, right? What does that mean? That means its closure is going to be a subset of 0 comma root, right? So yeah, I stated the theorem without proof, but the proof is essentially as difficult or easier than some of the exercises I've done. So given that I've taught you the methods, you can try them on your own. But yeah, by that theorem, it's going to be a subset of this. So we only have 0 and root 2 to check for. Now for 0, we have the lower, right? Yeah. So for 0, we have absolutely no point that, yeah. Yeah, so 0 has to belong to the closure because you take whatever you want. Let's see. So how do you show that every neighborhood has it? So the open intervals has to have it. That's fine. And the only other type of neighborhoods that have it are 0 comma something. And yeah, if it's greater than 0, that has by density of rationals or reals, whatever, it's going to intersect this open interval. So yeah, there you go. So 0 must belong to the closure. Now what about root 2? So in the lower limit topology, root 2 is not in the closure. Why? Because this is, well, let's see, root 3 if you want. This is an open set that contains root 2 and is not intersecting this open interval. So in the lower limit topology, the closure will be this. Yeah. But in the rational lower limit topology, there is no such open set like this. And you take a rational less than root 2, you're going to intersect it. If you take a rational greater than root 2, it's going to not intersect, not have root 2 in it. So there is no upper open set that actually allows you to violate the closure theorem. So in the other case, in the rational lower limit topology, it's completely the same as the standard topology. Okay. Now the other one. Yeah. For the other one, I think root 3 is, yeah, so so root 2 is included in either case now. It's only in the other side that we can actually remove it. In here, no matter what you do, it's going to intersect root 2 comma 3. And here, since 3 is a rational number, we can actually have 3 comma 4, right? So 3 can be excluded. So for both the topologies, it's the same closure. Yeah. Yeah. Question 18 can be tricky. Let's hope I don't screw it up. I am not going to check my answers probably. Yeah. So for A, the closure is the exact, okay, I'll just draw the order of square for convenience. So for A, we just have a bunch of zeros. It starts with, yeah, so this is 0, comma 0. This is 1, comma 1. And it's going this way, right? So it's going from this to here. Yeah. So this one first. Because an actual dictionary goes from this way, right? I tend to get confused a lot, but it doesn't really matter when proving things. But yeah, just keep that in mind. I do tend to confuse the dictionary order quite a bit. Anyways, yeah, we have 1 by n, right? So 1, 1/2, 1/3, 1/4, and so on. Yeah. Okay. So you take any point other than k, essentially k cross 0. What do you get? So yeah, you kind of always get a basis element. And can we be sure about it? Let's see. So for 1, actually 1 is included, right? Yeah, so 1 cross 0 is included, so we don't have anything to worry about. 0 is quite far away. You can just take anything you want. Yeah, the closure of A is essentially just A, so nothing changes. Same thing with 1 minus 1 by n, I believe. Let's just check. Oh, it's cross half. So 1 minus half, then 1 minus 1/3, 1/4, something like that. Yeah. So here, I think it's also B. Hang on.